I'm Rebecca Jiang, and in this paper we propose an approach for shape and motion optimization of rigid planar effectors for contact trajectory satisfaction. The performance of a robot is a matter of both its morphology and control. The optimal effector lies in the shared design space of shape and motion. In robotics, we generally select an effector without optimizing for an intended task and subsequently design a corresponding effector motion. But pre-selecting an effector reduces the space of feasible motions. To avoid this restriction, a number of works take an object-centric approach and optimize directly over contact locations and object trajectory. But these frameworks only get us part of the way to a manipulation solution. They output disembodied contact points whose motions need to be realized by a physical end effector. We propose a framework that does this. Our framework takes as input the motion of an object and contact points and contact tangents to manipulate it, for example, the disembodied contacts just discussed, and outputs an optimized rigid effector that meets these contacts without geometrically conflicting with the object or environment. In doing so, our framework encodes task-specific information into the geometry of the effector, reducing mechanical and control complexity relative to a manipulator that articulates to meet a contact trajectory. In this presentation, I'll describe how we pose the co-optimization of shape and motion of rigid planar effectors as a tractable nonlinear program. In particular, the solution is constrained to not intersect the object or environment, make contact with the object as specified, and optimize a user-specified objective. Appropriate shape representation is a known challenge in shape and motion co-design. As such, we implement a representation that can be integrated into our optimization algorithm, is sufficiently expressive, is conducive to posing constraints, and is tractable. I'll first address how our framework circumvents the need for traditional shape parameterization, a notoriously tricky problem. Let's take another quick look at our framework's output. Along with the shape of the effector, the solution characterizes the motion of the effector, represented here by a moving reference frame. With a candidate effector motion, we can fix a reference frame to the effector. Here once again is the motion of the effector frame from the solution we just viewed. Here is the same motion viewed from the effector frame. In this reference frame, the effector is static and the world moves around it. We leverage the key insight that the prescribed contact points, when represented in the effector frame, must lie on its contact surface. This relationship allows us to use these contact points to implicitly represent the effector's shape as a function of its motion. As a result, we can pose a nonlinear program to optimize over motion variables alone, while maintaining the ability to constrain the feasibility of and optimize characteristics of the effector geometry. However, not all unconstrained candidate effector motions lead to acceptable effectors. The derived effector may intersect the object and may not respect contact tangents. Watch as this motion results in an effector that intersects the object and has incorrect tangents. These two conditions can be detected and constrained using the object and contacts in the effector frame. We constrain that, in the effector frame, contact points have non-negative sign distance relative to the object at all times, and that the contact points approximate an integral of the contact tangents. We use a nonlinear program solver to find feasible, optimized solutions. We demonstrate use of an effector designed with our framework, along with the corresponding motion, to lift a screwdriver from a table. The precise forms of the upper and lower contact surfaces work in concert with one another to scoop up the screwdriver by the bottom corner, enabled by a downforce from the upper surface, which increases friction with the table. After scooping the screwdriver, the tool slides deeper onto the handle to grasp it. We demonstrate our method on a variety of problems. Here, we design fingers to scoop a disc up from a table without translating in the vertical direction. Our nonlinear program formulation allows us to model the table as an obstacle, constraining that the fingers do not intersect it. Notice, however, that the fingers intersect each other. We can prevent this by modeling an additional obstacle while still minimizing vertical translation of the effector. Our method can be applied to other design problems and can recover the well-known solution for the design of the rock climbing cam. This cam wedges between opposing rock walls, contacting the walls with constant contact angle, independent of their separation distances. As expected, our solution matches the known analytical solution for this cam shape, a logarithmic spiral. We can also handle objects that evolve. We design a tool that contacts circular objects of different diameters, for example jar lids, all with the same contact geometry. First minimizing total effector surface length, then minimizing the length of one effector surface, finding qualitatively distinct solutions. In summary, our method co-optimizes an effector shape and motion solution that does not intersect the object or environment, makes contact with the object as specified, and optimizes a user-specified objective. To accomplish this, we have represented effector shape in a way that can be integrated into our optimization algorithm, is sufficiently expressive, is conducive to posing constraints, and is tractable. Full details are available in our paper. Thank you.